sequences? Yeah, sequences. What do we mean by sequences? All right, that's a great question, right? So let's start there. Let's start there. What do we mean by a sequence? Okay, that's a great question. So a sequence. I'll give you a couple of examples, right? So a sequence is nothing more than a string of numbers put together, right? So this could be a sequence: 1, 2, 3, 4, 5, 6, yada yada yada. Now, the 3 dots on the end mean that the sequence goes on in the exact same fashion forever and ever, just as like what you see on the page. Okay, let me give you another one. Here's another one, right? We could do this. We go 2, 4, 6, 8, dot dot dot. That's another sequence of numbers, right? I give you another sequence. I can give you this one. I could give you 2.5. I could give you 5. I could give you 10. I could give you 20. Dot dot dot. Going on and on and on. Right? Can you guys make up a sequence? Make up any sequence you want. Give me another one. 3, 6, 9, 12. Dot dot dot. There we go. That's another sequence. Okay. So sequences are nothing more than strings of numbers put together in a certain arrangement. Okay. There are many different types of sequences, and the one that we're going to study in this particular section, 4.7, is all about arithmetic sequences. But before we can do that, I want to give you a little bit more background information about them. So consider for me, if you will, this sequence right here. We'll do 5, 8, 11, 14, dot, dot, dot. All right, so let's consider this particular sequence right here. I want to get a couple of terms or definitions across to you, all right? The way that we describe a sequence is in terms of inputs and outputs. So it makes a whole lot of sense to talk about a sequence right after you talk about functions, because arithmetic sequences are built from linear functions, okay? And so I want to make that connection between you two. So the way that we talk about a sequence is this term right here. This is the first term of the sequence. The letter A, it's a capital cursive A with that little subscript of 1, represents A sub 1. That is the first term of the sequence. So the number 5, the number 8, the number 11, the number 14, all of these are called terms. Okay? They're all called terms. That's the name that we're giving them. They're terms. Now we have to have a way of describing the location of the term. So as an example, 5 is the first term. So 8 is the what? It's the second term, and we describe that as A sub 2. 11 is the third term, so we would describe it as A sub 3. 14 is the fourth term, so it would be A sub 4. Well, and so on. What would this term over here be? Well, the any term that we're talking about, the nth term, we say that that is called A sub n. So A sub n is the generic nth term of a sequence, where n could be any one of these numbers that we're plugging in. So right now, it's a good place to consider the domain and the range, okay? The domain for a sequence are these positive integers right here, 1, 2, 3, and 4. So the domain, the inputs are 1, 2, 3, 4, so on and so forth, n, right? The range is the outputs. Those are these numbers up here, 5, 8, 11, and 10. So these are our range numbers, and these are our domain numbers. And the reason I'm making a big deal about this is because we're going to have to relate and write a rule for sequences. So when I plug in a 1, I want to receive a 5. When I plug in a 2, I want to receive an 8. So a sequence is nothing more than a pattern that's built off of a rule. And it makes sense to talk about sequences right after we talk about functions. Is this getting a little bit deeper for you in terms of what we're talking about sequences here? Okay, so the arithmetic sequence, which is the title of this particular sequence, or of this section, is a very special type of sequences. Okay, so let me give you an example of an arithmetic sequence. The last one that we saw was, so here's 3, here's 8, here's 13, here's 18, and dot, dot, dot. Okay, so why is this arithmetic? What makes it arithmetic? Okay, well, the first term is a 3, the second term is an 8, the third term is a 13, the fourth term is 18. All right, so what do you guys notice? 3, 8, 13, 18. Anybody notice anything?
It's by 5.
What do you mean it's by 5? I don't get it.
Adding 5.
You're adding 5. So if I go from here to here, I add 5. To get from 8 to 13, I add 5. To go from 13 to 18, I add 5. Okay, so what's going on here? What are we doing? How do we describe that in words? Well, yeah, I mean, there is a common difference, but I wouldn't see that as a difference. Do you guys see it as a difference? No, I see it as like a sum, right?
The change in what? The change in that is like universal in between.
Yeah, most people say, well, you keep adding the same number to it. And they're right. You keep adding the same number to it, right? But the way that we describe it is just what Bella says, okay? If you take any term in the sequence, and so far I only have 4 of these, I'm going to pick the third one. If I pick any term in the sequence, and that term is a value of 13, and I subtract off the previous term, minus 8, I am guaranteed to get that 5. That's where it shows up. So an arithmetic sequence is, the definition for us, is going to be a sequence with a common difference. Okay, it's a sequence with a common difference. Meaning that if I pick any term in the sequence, I can subtract off the previous term, and that result shall remain constant for any 2 consecutive terms, right? What do I mean by 2 consecutive terms? What does the word consecutive mean? One after another, right? One after another, right? 2 consecutive terms. So, okay, so let's do a couple of examples in the same box here to make sure we illustrate the point. So let me give you a sequence: 5, 11, 17, 23. You guys tell me, arithmetic or not? Yes or no? Okay, why do you say yes? You guys say yes. How come? Tell me why. The common difference would be what? The common difference would be 6. Okay, let's do example B. Let me give you this one. How about 400? How about 200? How about 100? How about 50? Dot, dot, dot. No, why not? Yes, the difference between 400 and 200 is 200. The difference between 200 and 100 is 100. The difference between 150 is 50. So that one will be no. All right, very good. How about C? Let me give you another one. Let me give you 2, negative 4, 8, negative 16, dot, dot, dot. No? Why not? Well, in this particular case, right, the signs are alternating. So the difference there is going to be messed up for us. So in this case, no. Okay, not good. Okay, let me give you another example. How about negative 15? How about negative 11? How about negative 7? How about negative 3 and dot, dot, dot? Yes or no? Okay, you guys are saying yes. Now, what would the common difference be? Now remember, I said pick any term that you want and subtract off the previous term. So take negative 3 and subtract off the previous term. So negative 3 plus 7, how much is that worth?
4.
That's worth a positive 4. So in this case, the difference is positive 4. So your difference could be positive. Could your difference be negative? Yeah, okay, it could be different. It could be negative too. Common difference, that's fine, okay? So we seem to be pretty good about describing whether or not a sequence is arithmetic or not. Okay, let's talk for a minute about this word called a recursive formula. So a recursive formula means that the sequence is built upon itself, meaning that if I know something about the previous term, I can then generate the next one. Okay, so if I was gonna work this term right, here's what I know, right? I know that a sub 1 is equal to 7. You guys know that part too? Is that pretty good, right? Okay, that's the first term, right? What would the next term be? A sub 2 would have to be equal to what? Yeah, it's 11, right? So it's equal to a sub 1 plus what number? Plus 4. Very good. You guys see that? Because a sub 1 is a value of 7, which gives me that. So what would a sub 3 have to be? a sub 2 plus 4, right? What would a sub 4 have to be? A sub 3 plus 4. So what's going on? Describe what you see going on in this particular case. Well, what do I mean by recursive? What I mean by recursive is this, right? I mean, like, okay, if I want the second term, I take the term before it and I add on 4. If I want the third term, I take the term before it and I add on 4. If I want the fourth term, I take the term before it and I add on 4. So if we just continue this all the way down and I say, how would I describe then the nth term? Yeah, what am I doing? What would it be?
Take the term before it.
Okay, the term before it. Well, how do I say the term before it? Ah, you guys get it. Awesome. A sub n minus 1, right? A sub n minus 1. That's the term before it. And then plus what? Now, what does 4 represent in this case? It represents the difference, right? It represents the common difference. So plus the common difference. So we have a way of describing arithmetic sequences in terms of a recursive formula, right? Any sequence I want, any particular term in the sequence is just the one before it plus the common difference. All right? Does that make sense? Okay. All right, so we have the next idea that we talk about is after we talk about the recursive formula, we have an explicit formula. So the explicit formula allows us to find any term that we want in the sequence. Now the recursive formula, we have to use the one before it. So notice that if I want the fifth term, I have to know something about the fourth term, the one before it. Well, the explicit formula allows us to fast forward up to any term that we want in the sequence, and it's given by this. So if I want a sub n, all right, any term in the sequence, a sub n, it's guaranteed to be the first term, a sub 1, plus the quantity of the term that I want, n minus 1 times d. All right, so notice here that this n right here matches that n right over there. Why does this formula work? Why do you suppose that this formula actually works? What's going on here? I just keep adding on. I start with the first term, right? So like for example, right, if I want like a sub 2, right, of a sequence. Well, it's whatever the very first term was, okay? Then how many differences am I adding on to get to the second term? No, one difference, right? If I'm in the second term, right? Think about this way. Stay here. Here, I'll give you 5, and then 7, and then 9, and then 11, right? So this number 7 can be written as 5 plus 2, correct? This number can be written as 5 plus 2 times 2, right? This term can be written as 5 plus what? 2 times 3. Do you guys see that? So this one is 5 times 2 times 1. This is 5 plus 2 times 0. So notice that this is the very first term. This is the second term. This is, where did it go right here? This is my third term. This is my fourth term. So it's kind of written, but you'll notice that that number is always 1 greater than that number. 2 is 1 greater than 1. 3 is 1 greater than 2. 4 is 1 greater than 3. So you'll notice that this number is always 1 greater than that quantity right there. That's why that works. You guys ever seen that part before? You think so? Okay, cool. So the great thing about this explicit formula is this allows us to find any term that we want in the sequence. So let me give you an example, right? Let's say that we have this sequence right here. Let's say that we have. Let's make up a good arithmetic sequence. What did it do? Let's see here. How about 10? Okay, I'm with you. 20. Oh, okay. 30. Okay. 40. Okay. This one's not so bad. This one's kind of predictable. Let me give you something else. Okay, it's a good idea though. Let me give you 3, 10. What will the next one be? 17. What will the next one be? 24. Okay, good. Okay, and so on and so forth. So this is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. I'm curious. What is a sub 97? Oh my gosh.
Why don't you just put 97 like that?
Well, that's what we're going to do. That's what it allows us to do. I'm not sure if everybody caught that, okay? So what I want is, I want the 97th term. I have no idea what the 97th term is going to be. The explicit formula allows us to quickly and easily determine what that 97th term is going to be. And here's how it works, all right? So we'll use blue. So I am curious as what is the value of a sub 97? It's the 97th term. Well, I know from this it's going to be the very first term, which is 3, plus the quantity of 97 minus 1 multiplied by the common difference. What's my common difference in this case? It's by 7s, right? Very good. Okay. Okay. So therefore, a sub 97 is equal to 3 plus the quantity of 96 times 7. All right, let's bust it out. Let's see here. 3 plus, who's got 96 times 7 for me? Anybody? 672? Okay, so the grand total that I'm looking for is 675. So the 97th term of the sequence is 675. And notice that we did not need to use the recursive formula to get there. We could use the explicit formula to tell us what that term is going to be. It's pretty sweet, right? Okay, so I'm giving you a sub n equals 32 plus n times n minus 1 times 22. Is that an explicit formula or is that a recursive formula? That's an explicit formula, okay? Can you turn that into a recursive formula?
I assume so.
Okay, let's do it. Let's see what we can do, okay? So, a sub n. A sub n equal to, okay, let's do 32 plus, all you gotta do is distribute in. So this is gonna be 22n minus 22. Does that make sense? Okay, so a sub n is equal to, what's 32 minus 22? 10. Yeah, 10 plus 22n, right? So a sub n, whoops, sorry, a sub n is equal to 22n plus 10. 22n plus 10.